We talk about the meaning of the DC biasing and small signal. This is something we usually overlook. When we talk about the small signal, we actually need to bias it, set a stage for it, right? To make the transistor in the saturation, for example. It's okay to be in linear, just depends on your application. Once we set up the stage, just like what you are seeing here, I make the VGS at 1 volt, then you can start input the signal you want to process. It can be the signal coming from the microphone, and then you try to amplify it. So the real signal applied to a circuit may be swinging between 0.99 volts to 1.01 volt. They are big voltage, but the difference, the swing is small. And that's what we call the small signal, 10 millivolt. Now you could have solved the full equation, right? For example, I, right, equals to W on L mu C ox divided by 2 VGS minus VT squared. You could have done this. You say, okay, when it is 1.01 volt, what is the I? Maybe 1.01 milliampere. When it is 0.99 volts, the current maybe becomes 0.99 milliampere. You could have done that, go through all this trouble if you like that. But this is not a good way. It does not give us insight. On the other hand, we say, hey, since we already bias it, and then we are only oscillating at the biasing point, we can just treat this, linearize this circuit, right? After we solve the biasing point, we can linearize the circuit, treat it as a linear circuit. We're not going to use this equation anymore. It will be just a current, voltage control current source and resistor throughout all the circuit. And we only play with this small signal, 10 millivolt. So that is what we end up last time, right? We say, okay, I have this transistor. This is a nonlinear transistor. And the current depends on Vg minus Vt squared, which is difficult to solve. You see that it's so complicated, we even need to think about whether it's on or off. But once I know that it's biased at this point, I apply the signal, then I say that I actually can just treat this as a constant slope, which I call the GM. For a certain input of the gate voltage, or a certain variation of the gate voltage, in this case 20 millivolts, right? When it's smaller, then the current will also vary, right? It changes from 0.99 to 1.01 milliampere. So if I have 20 millivolts change of input, my output changed by 20 milliampere. And this equivalent to 1 millisiemens, which is 1 minute 1 over ohm, right? Is this okay? And that is what we mean by the small signal. I change this a little bit, the gate voltage a little bit. It tells me how much the drain current will change, right? Similarly, when we were dealing with the output, the output, we also care about the output resistance. For example, to describe this curve, which is ID and VDS, it's telling us what the drain current will change when I change the VDS, right? And we know that this region is the linear region or trial region. This is the saturation region. Because after this region, I have VDS larger than VGS minus VT. Right? We already spent time on this. If you forgot why, that is fine. The point is need to memorize when it is in saturation, right? So it is when VDS larger than VGS minus VT. So, okay, so this is the saturation. Where is the equation describing this region? It is in saturation. It is the same equation, W on L, mu C ox divided by 2 VGS minus VT. And you see that it does not depend on VDS, right? But then we say, in reality, it does depend on VDS. And how does it depend on VDS? We multiply it by 1 plus lambda VDS, which is the channel length modulation. right? So when here is when lambda equal to 0, here is lambda larger than 0. So again, you can just solve this equation for any input, but that is not what we want. We want to find out what is the effective output resistance. So we are going to do this, like what we did before. For example, we bias it at this voltage, okay? And we can change the input voltage, right? You can call it input or output, right? We change the VDS. Again, I say that maybe I change it by 20 millivolt peak to peak. I do the same thing, like what I did for the VGS. Then if in that case, what will happen to the output current? Well, it's going to again swing about this line, right? So my drawing is going to be very bad, but you know what I'm talking about here. Right? It's completely off, right? So what I'm trying to say, when you have a high VDS, you will have a high ID. When you have a low VDS, you have a low ID. Is this okay? Just along that curve, right? So now I will say that maybe this changed by 1 milliampere, maybe 2 milliampere. Let me call it 2 milliampere, 2 microampere. Okay? So what is the effective output impedance? Think about this. I have a voltage source. I try to change it by 20 millivolt, and I try to see how much current it will change. By definition, the R out is just equal to the delta VDS divided by delta, what is that? IDS. This is not transimpedance, right? Because it's talking about the same terminal, right? I look at this D. I change the voltage here, and I try to see how much voltage, how much current it changed. Just like a resistor, I give you a resistor, I ask you, what is the resistor? You say, okay, let me measure the current, and let me apply voltage. And this voltage is the delta VDS, and this current is delta IDS. And then you say, hey, the resistance equals to delta VDS divided by delta IDS, right? That is how you find a resistance, correct? Find the resistance. So I'm doing the same thing, although this is a complicated stuff, but doesn't matter to me. I only see one terminal as an electron. I change the voltage, and I see how it changed the currents. So what is the output impedance of this circuit? I change it by 20 millivolt, and then I get 2 microampere change of current. So what is the output impedance? 10, what is that? Kilo ohm, right? I said we reviewed earlier, milli means 10 to the power negative 3, micro negative 6, narrow negative 9, right? So this is 1,000, it gives you kilo, 20 divided by 220 at 10, right? So this transistor has an output impedance, R0, which we usually call it R0 also, equals to 10 kilo ohm. Now that is the meaning of the small signal. Is this clear? Now then, what is the point of doing this? I already told you that to do this is because I don't want to deal with this complicated equation. How? I will explain a little bit more, but I want to go to this transconductance first, right? This is a very important concept. So as I told you, when we care about transconductance, do we put it in the linear mode or saturation mode? What is this equation for? Saturation, okay? Saturation. We care about the saturation, okay? So I hope that you understand everything is saturation in this class, okay? So what is GM? We just show you it is equals to delta V. Can you tell me what is that? I want you to memorize. What is GM again? Transconductance is what? Delta I over delta V. What is I? Which I? You have three terminals. Which I are we talking about? IDS. And which V we are talking about? VGS. Because it's trans, so it needs to be different terminal, right? We're talking about, I turn on the switch on the wall, how much current will flow through the lamp, the light. That is the transconductance. I do not directly touch the light. I touch the switch, right? Something like that, okay? Which is just equal to the partial derivative of IDS on VGS, right? And what is IDS? Just copy the equation, W on L mu COS divided by 2 VGS minus VT squared. This whole thing is IDS, partial VGS, correct? And what do you get? The only dependence variable is VGS. VGS squared, I take 2, right? I take the 2 out, so this becomes W on L mu COS VGS minus VT, right? Because I differentiate again VGS, so this 2 will come to here. And this is the same as what I put here. Now, so here we use the graphical method to show you what is GM. But you don't want to do this using your hand. This has an equation. It tells me that if you bias at this VGS, how much GM I will get. It depends on VGS. That is the main point, right? Depends on VGS. All right, so we set the stage. How strong the transistor is depends on the VGS that you apply to it. These three equations are equivalent. Please go back to derive yourself. All you need to do is just substitute the appropriate equation to it, right? Because instead of putting VGS, I want to use IDS. Okay? So GM is very important. We will see that later, right? As a circuit designer, what can you change to change the GM? Based on this equation, what can you change to change the GM as a circuit designer? Say again? Oh, someone say W, L, because you do the layout. Very good. And what else? Huh? Someone say ID, right? It's the same. You can say ID or VGS. This you decide how to bias your circuit, right? But you cannot change the COS and mu. Again, unless you own the factory, the foundry, or you are a super big customer. Like Intel. Intel, they do it themselves. Yeah, you're right. Yeah. Okay, so here is a way to double the GM, right? Because GM is important, so we have this slide to talk about this. If I have a transistor like this is its width, right? I hope that you're very familiar with the transistor picture now. This is a 3D picture. This is the width. This is the length. This is source. This is drain, and this is gate, right? I just make 2 of them, or I can make it longer. The point is that I make them in parallel, right? This is still source. This is still drain. This is still gate. But now I have doubled the width because this is W, this is W, this is L, this is L. It's just that for the freeway, I double the number of links. That's it. And then my transconductance will be double. Yeah, because now it becomes 2W, so GM will increase by 2x. Right? Very, very simple way to make a larger GM. Is that okay? Okay, then how about the output resistance? Output resistance, again, I show you how to get it from the graph, right? But now we want to let's try to derive it, what it is. By definition, R out, R0, we already discussed, is about if I give a certain VDS change, how much is the change of IDS, right? Is this okay? Just very straightforward. I give you a resistor, find the resistance, add a voltage, and then find the current change. That is the resistance, right? But now we need to use the equation, right? Again, this is just like the GM. Like in the GM case, this delta needs to be very small. So I just use this partial VDS partial IDS, okay? And we know that this is not straightforward, so I'm going to just find the inverse of it. Partial IDS divided by partial VDS. So what I'm doing is instead of partial V, partial I use partial I, partial V, but then take the inverse. And why is that? Because you need to find that relationship, and you find that you have this relationship. ID equals to W on L mu C ox divided by 2 VGS minus VT square 1 plus lambda VDS. Right. So you can shuffle them, but I prefer to do this because I is in terms of V, so it's easier to find what is partial IDS, partial VDS, right? Okay, so what is this? I only have a dependence variable here, VDS. I don't have others. So this is equal to W on L. They just like a constant in this differentiation operation. And then the whole thing times lambda, right? Because what is the differentiation of this one? This is lambda, right? With respect to VDS. And this is just like a constant in this operation. Now, so this is not easy, but we can say that because usually in a normal transistor, the lambda is going to be small. So we can say we can ignore this term, right? So what we're trying to say is that this one, the whole thing, is just like ID times lambda. Because this term is very similar to this term, except that this term does not have 1 plus lambda VDS. But this is small usually, so it's a good approximation. Okay? And based on this, we plug into this equation because R0 is 1 over this term, right? R0 is 1 over this term. So I get R0 equal to 1 over lambda ID. Right? Here I get partial ID partial VDS equal to ID lambda. But R0 is 1 over the whole term, right? So this is 1 over lambda ID. Okay, so that is another equation you want to memorize. And it is very normal. When lambda equal to 0, do we have channel length modulation? We don't have channel length modulation, right? When it is equal to 0. Maybe, let me change it. Then what is RL? R0, I mean. Infinity, right? So when you don't have channel length modulation, you have infinite output impedance, which is the ideal case that we want. Okay. So go back to, or if your question, let me know now. Otherwise, the point is that we extract two very important parameters. One is GM, one is R0. They are small signal, remember? Because they are the partial VDS, partial IDS, partial IDS, partial VGS. Graphically, it is the slope or inverse of the slope of this thing. We use this tool and then we try to model the transistor. And that is the summary, right? So we have this curve. This transistor is very complicated, but its characteristic can be represented by this curve. We bias it at a certain VGS, certain VDS. Then we will only care about the slope at that point. And from there, we will build a small signal model. So this complicated transistor now becomes, although you think it's more complicated, but actually this is simpler. It has two more elements, that is true, but they're all linear. This is voltage control current source. You change the gate voltage, then it tells you how much current you have by what? By GM times the voltage. Because you remember, GM equals to partial IDS partial VGS. So the small signal IDS is just equal to GM times VGS. That is what it's trying to say. And similarly, the output impedance is represented by this. Okay, I will go to more detail, but this is the whole picture. Let's zoom in, right? Now we have the small signal model. We bias it at the DC, and we don't care about that anymore. We know that it's in saturation. But under certain bias, it has a certain GM and also a certain R out. So how do we represent this GM? Which is talking about how the current changes. But so let's take a look, right? So in this so-called small signal model, we have a small VGS. So what is the meaning of this VGS? If you look at the total voltage, the total case, including DC, what it means may be in the transistor, I apply 1.1 volt. I apply 1 volt to VGS. To the gate, apply 1 volt. And then later it changed to 1.01 volt. And then you go back to 1 volt. And then go to 0.99 volt. This is the total one. Like here. 1 volt. And then between 0.99 and 1.01 volt. Okay. The VGS, the small signal VGS here, is representing that, okay, you are at your DC bias, so I apply nothing to it. Then you change it to 10 millivolt, and then nothing again, and then negative 10 millivolt. That is the meaning of this VGS. So when we look at this, we know that I already biased it at a certain voltage. Here is only the difference, the fluctuation. Okay? So is this model correct? Yes, because this model tells me that by changing this small VGS, I will get a change of the IDS. And this circuit tells me that IDS equals to GMVGS. Correct? Because that is the function of this element, right? This IDS equal to GMVGS, right? So it means the GM equals to IDS divided by VGS, which is exactly the same as the definition of GM. That GM equals to delta IDS divided by delta VGS. That you get from this curve. Okay, here just to show you that this is a valid model. Indeed, if I have a small change in the gate, I will get a small change in the drain current through the relationship IDS equal to GMVDS. Okay? Now then I add one more element to it called R0 in order to model this channel length modulation. So let's take a look again. What is the meaning of the change of VDS? This might be 2 volts. And then I apply some small signal. Maybe this is 2.0. It changed to 1. Why? This one is 1.99 volt. And then when you apply a larger voltage, 2.01 volt, right? So the total VDS, how does it change? It changed from maybe 2 volts and apply a signal become 2.01 volts. And then you go back to 2 volts and then become 1.99 volt. But from the small signal point of view, VDS, you change from where? 0 volts because it is the DC bias. I did not add anything. It becomes 10 millivolts. Go back to 0 volt becomes negative 10 millivolts again. Is that okay? Because for small signal, we're talking about the difference or reference to the DC value. Yeah? So is this model correct? The first of all, something we have not learned yet, the so-called output impedance is equals to V out divided by I out when the V in equals to 0. So in order to find the output impedance, we will need to ground the input and then find how much current it will go in. Okay? But when I ground the inputs, then it means this is 0 because VGS equal to 0. So GMVGS is 0. So there's no current going in there. Right? So from the circuit, I do see that the output impedance equals to VDS divided by IDS equals to R0. Because this is only resistor I see. Right? So it modeled this correctly. This is a little bit confusing. Maybe it has some looping there. But in summary, I hope that at this stage you understand what we are doing. We have a transistor which is not linear. We try to bias it at a DC point. And then we only need to discuss how a small signal changes its characteristic. And from there, we just need to have a very simple model like this. Linear out, linear voltage control current source. By using this one, then we can ignore the DC. But GM and out actually depends on the DC bias. And then from here, we just play with this small signal. 10 millivolts, negative 10 millivolts. It's okay to have a negative value because so-called negative value, it is just saying that the total voltage is less than the biasing point. Any questions? No one is going to test you this in the future, maybe. But if you understand what I'm saying or understand how bad I'm explaining, then That will help you to appreciate what is the meaning of small signal. Because from there, in the future, when you get a new device, you invent a new device, someone come to you with a new let's say neuromorphic device, ferroelectric device. You know that what you need to do the small signal analysis. Okay. So we know what is the small signal for NMOS. Now I want to spend some time to talk about the small signal circuit for the PMOS. And it is very easy. On the top right is the small signal model I just gave you for NMOS, but I flip it. Just look at this. Source, right? And then you have drain, have this current going down, and you have this resistor,